viewers. This is Amazing Maths, where we demystify, challenging math problem. So here is a question for us to work on. Find the area of a rectangle. So first of all, I would like to draw the rectangle because it's always good to draw a very good diagram so that will help you to actually see, exactly what you need to see. So I'm drawing a rectangle there. So I need a square. I need a circle. So I'm going to draw my inscribed circle in the rectangle. So I hope this help out. Okay. So that is my circle. I want to ensure that the circle is actually inscribed. I think I should increase the size a bit. Okay, so this is a life solve fresh problem. So let's see how we do this. Okay, so that's the circle there. Just like you can see, the center of the circle is at the midpoint. So let's call this the midpoint of the circle. Sorry, let me use a faint pen. So pick a different color. So that's the center of the circle, and you observe that a line passes through. So I'm going to draw a line. So the line starts from the tangent of the circle with the rectangle at this point. It goes all the way down to this point, right? Okay, so we have that first. Then what else do we have? So we have that from here to that place is 6 units, and from there to that is 5. So we have to find the area of the rectangle. We know the area of the rectangle is the length times breadth. So we know by definition, area of any rectangle is the length multiplied by the breadth. So the length is the distance from here to here. So that's the length. While the breadth is the distance from here to here. So now, what are some of the key observations that we observe? So we observe that if you draw a line, so let me just draw a line. So if you draw a line from here to meet this tangent, tangent is where a curve or a circle touches a straight line. So here is a tangent. So if I draw a line from that point, center to that tangent, and drawing another line again. So this was an observation from the tangent below. So we can actually draw a straight line. Now this straight line from the center to each point of contact of the tangent is actually the diameter of the circle. And we know that if you draw a line from the center to meet a tangent, is always at 90 degrees. So another observation is that this is going to be 90 degrees, right? This angle here is 90, and this is 90. Because this is already a rectangle, so this angle here is already 90, and this angle is 90. So this is another rectangle. So this means these two sides has to be equal. Now that means the breadth of the rectangle has to be the diameter, the length of the diameter of the circle, which is also equals to 2r. So that's the first thing that we can deduce from this diagram. Okay, so we don't really have much information on how to find the length. Neither do we have much information on how to find the breadth. So one of the things we are going to use is that we are going to see if we can see some relationship between some of the side lengths or the length of the line segment in this diagram. See if we can establish a relationship that will enable us to find the length in terms of a particular side length that we don't know, and so probably that will help us. So how do we go about that? Now, if we draw a line from, so let me change the color of this. If we draw a line from here, so I'm just going to draw another line again. So let me use a black color. So, so let's try and observe that. If you draw a line from here, from this tangent at this point, so that the line passes through the center to the other end of the what do you call it, the rectangle, the other side of the rectangle, such that it meets it at 90 degree. So let me just indicate the angle here. I'm using a green angle for that, green line for that. So this angle here is green. Okay, green just denotes the right angles. Now we can actually do some nice, use some nice properties that we know about circle. So we know that this is going to be a right angle triangle. So I'm just going to label them, but before I label them, I will do some observation. So I can draw another line segment from here. Um, so I'm going to draw another line segment. So let me use a green, a black. So from this point where it cuts the circle, so I'm drawing another line segment. Sorry, I need a line segment for that. Okay, so I'm drawing a line segment from here to meet, um, yeah, so something like that. Okay, so now from what you know about circles, if you look at that, you see that, you observe that this, so let's label it so that things becomes, we can work, it's easier to work with label diagram. So we want to call this, so let's call this angle. So you can just give a random angle that you want. So let's call this angle, let's say this is angle A here, or if you like. So let me get rid of, so let's just call, give it angle. So let's call this angle A. So let's call this point A. Let's call this point B. So we'll call the center of the circle C, and let's call this point E. Okay, so it's good we work with label diagram. So let's call this F. So that point is F. Okay, we can also draw another line segment from this other point where it cuts the circle to, sorry, trying to draw a better line segment. So from this point where it's cut the circle, so imagine we draw a straight line. I'm going to move it a bit. I think it's better position like this. Okay, this is okay. So I'll label this angle again. So we are drawing a lot of straight lines. So this is another 90 degree. So we just relabel it so that we have enough space to indicate our points. So A, B, C. Okay, I missed one letter actually. So this should be E. Sorry, D. So A, B, C, D. So here should be D. So let's call this E. So let's call this F. So let's call this G. Okay, so we have that established. We have that established. All right, so now so that is the first thing that we have established. Like I said, we want to see how to see a relationship between the length and the breadth. So if you observe very well, you discover that there are so many right angle triangles. Okay? So there's a reason why we are doing this, because we want to establish a relationship between the breadth and the length. So now, uh, according to the inscribed angle theorem, circle theorem, whenever you have a triangle that is inscribed in a circle such that one of the side of the triangle is the diameter of the circle, then uh, that side is actually the hypotenuse. So it's actually a theorem in circle geometry. So I believe you might have heard about it. It's called the inscribed angle theorem. So this angle here is going to be 90. Okay, so remember the 90-degree angle is just the green angle. So it's not, I don't need to draw it. So that's just identify that angle there to be 90. So triangle BDF is a right angle triangle, right? So same for triangle AGD and triangle AGF. So we have a whole lot of right angle triangles. So our goal is that, can we do any comparison? And for we to do comparison of triangles, we need to find out if these triangles are actually similar. And the criteria for two triangles to be similar is that they uh, they must have two angles that are corresponding and they are equal. So let's do some angle chasing. So now I'm going to use a red angle for. So now this angle here, let's call this angle red, is corresponding to this angle here, right? Because these two lines are parallel, so these two angles are corresponding. Then let's take another angle. So I'm going to use yellow. So this yellow angle here, okay, is so the yellow angle there is definitely going to be, so yellow plus red will give you green, right? So in triangle BFD, if you add angle yellow plus angle red, you get angle green, because angle green is 90. So that means that if we look at triangle EGF, that means this angle has to be yellow. Okay, even though you can't say if they are corresponding or not, but from the sum of angle in a right angle triangle, if one angle is 90, then the sum of the remaining other two has to be 90. So this has to be yellow. So now we have some useful, nice relationship between all the triangles in the triangles. You can see that most of the triangles we have here, they have something in common. So let's try and apply our similarity ratio. So so with this we can actually make the inference that this triangle. So let me start with the biggest right angle triangle, which is triangle, I think, so triangle AGD. So why I'm choosing this triangle AGD is because it has a side length that has the length of the rectangle. Is similar to triangle EGF, which is another right angle triangle, which is again similar to triangle BFD. So so what we're going to do is, since the breadth of the since we are looking for the area, recall that the area of the rectangle is the length times the breadth. So, and since the breadth is big 2r, as we've shown earlier, so it means that the area is going to be 2rl, right? If you replace the breadth with the with 2r. So even though we cannot find them individually, let's see if this relationship will help us to do that. So what I'm going to do is that I'm going to use my similarity ratio. So I'm going to start with establishing similarity between EGF and BFD. So for EGF, now also why we have to choose this triangle is because GF is 5 from the diagram. So if from here to here is 5, you can see it from diagram, and FD is 6. So we are choosing this triangle, hopefully that to be a better choice for us. And I also see that all these triangles, they're actually built out from the two triangles, EGF and BFD is built out from AGD. So that might be a very good connection for us. So let's see the relationship between EGF and BFD. So using the similarity ratio, so we'll just take it in terms of their corresponding. So the corresponding angles, size of these two triangles is 5. So 5 over, so we just have to look at where the green angle in the other triangle. So 5 over BD, and BD is 2R, because they are similar, must be equals to. So we just take another length. So let's say we want to take, let me see. So let's say the yellow. So the yellow is EF. Yellow angle is facing EF over, um, so EF over 6, because the yellow in that triangle is facing 6. Okay, we don't know if this will be okay to, or let's just take another equivalent, equals to the red. So in EGF, the red angle is facing EG, so EG over, and the red angle is facing BF there. So let's just call this equation 1. So we'll take another corresponding. So we'll now find relationship between AGD and BFD. So let's see that. So what's the relationship we can deduce from here? So for AGD, we have GD, which is the longest side of, that's GD is 5 plus 6, that's 11. So 11 over, okay, so let's find the relationship between AGD and EGF first. So 11 over 5, okay. Now let's find the relationship between EGD and BFD. Okay, let's do that first. So 11 over 2R, I think so. Yeah, 11 over 2R is equals to, so let's go to the yellow. So the yellow now is facing AD, and AD is the whole length. So that's L over, so let's look at yellow is facing 6 there, equals to, so the red is facing AG over BF, I think so. Yeah, BF or FB. So that's 2. So with this useful property, what can we so what can we do with this? Okay, let's look at this critically. So what can we do with this? Okay, what can we do with this? Let's see this. Okay, so let's take another useful property. So now let's compare EGF and BFD. Now, so EGF and BFD. Oh, we've done that first. So now let's compare. So I just AGD and EGF. So let's do that. So that's what I want to do now. So if you do that, AGD, that's the green angle is facing GD, that's 11 over the green angle is facing 5. So 11 over 5 equals to L, which is the yellow angle facing L, over EF, right? Yeah, equals to AG, which is the red angle is facing AG, over the red angle there is facing GE. So we'll call this equation 3. So with these three equations, now if we multiply um, EF, what happens if we multiply EF over 6 by L over EF? So it's going to be the same as, so we can use the similarity ratio now, multiplying 5 over 2 by 11 over 5, I think so, right? Isn't it, from the similarity ratio? Yeah, so that's what we have. So when you do that, EF will cancel EF, 5 will cancel 5. So we now have that L over 6 is equals to 11 over 2L. So that means 11 times 2L is 66. We're done with the problem. So that's the area of the, no, the area of the rectangle. So the area of the rectangle is what? 66 units. So you can see how that's a very good diagram, and knowing the relationship, how the relationship between the triangles relates to what you are looking for, how to, identify those triangles were so cool for us to solve this problem. So kindly like this video, share and subscribe, and see you again for another episode of problem solving in maths. All right.